So that's going to be what we're trying to do. Okay, so what would that look like? Well, let's say we have our axis there, and let's say that we have two curves. I'm gonna try to make them a little bit big. There's gonna be one. Let's say the other one will be somewhere here. Oh, I didn't quite get to connect. Let's say we have those two curves. This one's gonna be given by y equals, let's say, f of x. And let's say that this one is given by y equals g of x. Two different functions. And let's say we want this area between these two curves. Okay. So what we're gonna need is first, well, the first intersection point is gonna be, let's call it A, and the second one is gonna be called B. And what we would do is, if we want to compute the area, we could partition this and do our rectangles, where the height of each rectangle, let's say we're going to do it on the right, would be given by what? Well, let's take a look at what this height will be. If this would be x1, x2, x3, this height here is going to be the value of the function. In this case, the green function is g of x, 3. And this height is going to be f of x3. So that height of the rectangle would be f of x3 minus g of x3. That's going to give us the height. So, okay, so as we were saying, the height then is going to be the difference between f of xi minus g of xi. So just the difference between the heights. So our area will be given by the limit. I do right sums because it's easier. As n goes to infinity, of the sum of I equals 1 to n of delta x. I'm going to take a uniform partition, so I don't have to write delta xi, and then f of xi. I should have done f of xi minus g of xi, because that's going to be my new height. And so what does that represent? That represents, this is going to be my width. It's going to be the width of each rectangle. That's going to be our delta x. And then this difference is going to represent our height, the f of xi minus g of xi. And then if we go ahead and compute that, or write it in terms of our integral, this would be the integral from a to b of the difference of f of x minus g of x dx. So another way to see this is the following. If you compute your integral, if you split it out like this, you could split it out as a to b. This is the way we're going to compute it, but to see what it means, we can write it like this: f of x dx minus the integral from a to b of g of x dx. So what that's telling you is you basically are computing the area under the curve for f of x, all that, and then you're removing out the area under the curve of g of x. And what that leaves you with is this area right here. So our formula then is going to be this one right here. So let's go ahead and compute a few examples. So the area under between the two curves is going to be the integral from a to b, where a and b represent the intersection points, or whatever intervals were given, or endpoints for the interval that were given, of the subtraction of the function on top minus the function of bottom. Now, be aware that this could also, the following situation could happen, where you could have a function that does something like this, and the other function does something like this. And they don't have to necessarily intercept. You could be told to go from one interval to the next. But if this red one represents f of x, and the white one, or whatever that color may be, is g of x, then you notice that there's two different behaviors. So from A to B, you get that area here, so let's call it area 1. So area sub 1 is going to be the integral from A to B, and at that point, for that function, for that region rather, the function on top is going to be f of x. So you put it first, and then from B to C, if you will, then the behavior changes. So you'd have to go from B to C. But now you don't do f minus g, because the one on top is no longer f. Now it's g. So if the behavior of the functions changes, you'll have to write multiple integrals and partition your big interval into smaller intervals, so that you're always subtracting top minus bottom, so that because what that means is that heights you're computing are positive, so your area is going to be positive. Once you move to this side, if you were to leave it as f minus g, this area would be negative, and you don't want that to be negative. So I started with a sub 1, and I messed up there. The area was a. This right here represents area of 1, and this one right here represents the area of region 2, right there. All right, so let's do a few examples, and then we will close this video after a couple examples. All right, so this is probably my favorite example to start with areas between two curves. It resembles a lot what I drew at first, as you have y equals x squared and then square root of x. All right, and so what we need firstly is to find these intersection points. So to do that, we set the two equations equal to one another. So intersections you said x squared equals to the square root of x, which is x to 1/2. So you can square both sides of this, and you get x to the 4th when you square the square, equals x. And then you go ahead and subtract x on both sides. You don't divide by x. Why do you not divide by x? Because if you divide by x, you get x cubed equals 1, and it just gives you a single solution. And in reality, this has, there has 3 solutions of interest to us, but in reality, this is a quartic polynomial, so it would have 4 solutions. So let's go ahead and take a look at what happens. So we subtract that there, and we go ahead and factor out an x. I said 3 of interest. It's going to be 2 of interest, and there's 2 more that are complex that we don't care about really. So I misspoke there. However, when we factor that there, I'm going to continue to this side to not take the whole space, just doing intersections. We get either x is equal to 0, which is 1 point of interest, which is this one right here, the origin, or x cubed minus 1 equals 0. Now, this one has 3 solutions, but 2 are complex. The only one we care about is when we get x cubed equals to 1. And that's the one I was mentioning. When we take the cubic root, we get x equals to 1. Now, there's 2 more. And if this were, for example, x cubed and x to the power to 1/3, then we would even get more solutions. So that's the one I was thinking about. So we have 2 points that we care about. So just set them equal to each other and find those solutions, but be very careful. Whenever you end up with an equation, do not divide by x, because if we would have divided by x, we essentially would have eliminated this root right here given to us, which is x equal to 0. Of course, from the graph, you could have seen it as well, but we now have it, and we solved it algebraically. So that's what we needed. So we have the interval we're going to be working is from 0 to 1. So the area, now, this is the easy part. Once we did the solving, it's kind of funny that the integral part is the easiest one. or should be at least, is going to be the integral from 0 to 1. And then the difference, the top function here is the square root, which is kind of funny, but between 0 and 1, the square root of a number is larger than the square of it, because when you square it, you make it smaller if you think about it. And then so you get the square root minus x squared and then dx. So now it's a matter just of calculating this. So it's going to be the integral from 0 to 1, and remember the square root is going to be x to 1/2. So we can use our power rule there. X squared, that one poses no trouble. And so we get that the integral there, you add 1, you're going to have x to 3/2 over 3/2 by adding 1, minus x2, you add 1, is 3 over 3 between 0 and 1. Now this is going to be 2/3 of x to the 3/2 minus 1/3 of x cubed. So when I evaluate between 0 and 1, I plug in my values. I get 2/3 times 1 to the powers of 3/2, that's still 1, so I'm just going to write 1, minus 1/3 times 1 to the power of 3, or 1 cubed, which is still 1, and then minus, and I ran out of space, but minus, and I plug x equals to 0 here. That's going to be 2/3 times 0 is 0, minus 1/3 times 0 is still 0, so that's 0. And I get that this is going to be 2/3 minus 1/3, which is 1/3. And that's the area between those two curves.